Hello everyone. In the previous tutorial session, we implemented spectral based graph filters using the PyGraph signal processing package. We dealt with Fourier transforms and we converted the graph from the vertex domain to the spectral domain, implemented traditional filters like the low pass filter and data driven filters like the Chebyshev filters, which deals with k-hop neighborhoods given the order of the polynomial. There, we randomly initialize the parameters theta and use the randomly initialized parameters to filter the signal in the spectral domain. In this tutorial session, we will be dealing with multi-channel graph signals. Unlike the previous tutorial where we had a scalar value associated with each node as a feature, here we deal with the feature vector for each node, which is also known as multi-channel graph signal. And we'll be learning the parameters with the help of a package called PyTorch. I'll be importing the package here, and we'll also be implementing graph neural networks based on the torch geometric package, which is a package that deals with graph structured data in specific and built on top of PyTorch, which makes our life easier. It has an array of convenient functions and filters like the GCN conv here, graph attention conv, graph sage conv, and also pooling layers like the global mean pooling here. And in order to deal with training the model per se, we'll be using the PyTorch Lightning package to structure our code and deal with back propagating the loss calculated here. PyTorch has an implementation called AutoDiff that so initially when you perform an operation in PyTorch, it makes a graph, an internal computation graph, and then back propagates the loss towards the graph to perform automatic differentiation. So in order to learn these parameters, we need to implement all the functions in terms of PyTorch here. Let's see how to implement the degree matrix in terms of PyTorch package here. That we take the adjacency matrix as input and we calculate the sum along the rows or columns and we create a diagonal matrix here. Run this. And PyTorch also deals with a specific data structure called tensor, which is an immutable matrix and gives us a convenient way to perform matrix multiplication in a more efficient manner, and also can be implemented for computation in the GPUs, which is much faster than traditional CPUs. I'll be converting my existing adjacency matrix used in the previous tutorial from the graph to a PyTorch tensor here. And this, let's see the shape. It's 25 cross 25. And let's see how the matrix looks like. This is our matrix. Again, in the same way, in order to calculate the Laplacian matrix given the adjacency matrix as input, I'll first calculate my degree matrix and take the difference with the adjacency matrix. It's D minus A here. Since there are many numerical instabilities with just using the Laplacian matrix alone, I'll be using the normalized Laplacian matrix to perform my computation here on. I'll take the normalized degree matrix to the power minus 1 by 2 and perform matrix multiplication using the torch.maxmal function here. The shape is 25 cross 25 and this is your normalized adjacency matrix here. To implement the Chebyshev filter from the previous tutorial and also have learnable parameters, I need to calculate the maximum eigenvalue of the normalized Laplacian matrix. Let's see how to implement it. PyTorch also has a linear algebra module which helps us compute the eigenvalues and eigenvectors given a matrix as input, and I'll be using the torch.max function to return the maximum eigenvalue. The maximum eigenvalue for this matrix is 1.38, and let's see how to implement the Chebyshev filter using PyTorch here. I'll be initializing the list of Chebyshev polynomials, an empty list. I'll be assigning T0 to my feature matrix, in this case X. I'll calculate the number of nodes based on the shape of the adjacency matrix and with the shape of the adjacency matrix. Every operation that PyTorch performs is associated with a gradient. Whatever operation you do gets converted into the computation graph for backpropagating the backpropagating the gradient for the respective parameter. But since calculating the Laplacian matrix, finding the maximum eigenvalue, rescaling the Laplacian matrix does not involve any parameters, we don't need to backpropagate the gradient through these functions here. That's why I'm writing a line here called torch.nograd. Anything under this block, we won't compute the gradients for it. First, I'll be multiplying T0 with my first parameter theta 0. I'll be appending to my it to my list here, the parse list. T1 will be the rescale Laplacian matrix multiplied with T0. I'll append T0 multiplied with theta 1, and for orders greater than 2, I'll be running this loop, which is similar to the loop that we saw in the previous tutorial session. I'll stack the list. Stack is a function which stacks your list row by row according to the dimension here, and I'll be summing out all my polynomials. You can also concatenate it and bring it back to the original dimension, and that's your design choice. That's again a hyperparameter. You can take the summation, you can take the average, you can concatenate and bring it back to the original shape by using a linear layer. And let's test the function here. We have 25 nodes, and each node is associated with a feature vector of size 5. And I'll generate a random feature vector here. I'll set the order of the polynomial to be 5. So the information is aggregated based on the 5-hop neighborhood. Let's take a specific node. I'll look at my neighbor with distance 5. I'll aggregate feature from that neighbor, and basically the order tells you how informative your resulting feature set will be. If you increase the number of order here, you have to deal with more parameters, and as the graph grows larger in size, that's difficult to deal with. But higher the order, better the information capture, and higher the order, more number of parameters. It's always a trade-off here. And accordingly, based on the order, I'll be randomly initializing my parameters here to test the function. I'll run the function here. I'm dealing with multi-channel graph signals here. So each node is associated with a feature vector of size 5 here. I'll be setting the order of the polynomial to be 5 here. So the filter deals with the 5-hop neighborhood. I'll aggregate information from my neighbors with a distance 5. And if the order grows in size, let's say if I take the order as 10 or something, it can actually incorporate most of the graph structural information into the feature learning process. But again, if I increase the order, the number of parameters will become large. And for larger graphs, if you keep on increasing the orders, you have to deal with more and more parameters. So it's always a trade-off between the order, and the information in the feature learning process. I'll be initializing my parameters based on these order here, and let's test this function. This is my output here. Let's see the shape. Since my order is 5, I'm getting 5 here in the dimension output. Let's see, set it for an order 3. Let's run this function here. Let's run the function here. I have my nodes, 25 nodes here, and 5 is my feature vector. And if you look at the feature vector here, it will be much more informative than the randomly initialized feature vector, since it also incorporates the structural information in the learning process. Moving on, we'll be implementing the graph convolutional neural network, which is basically your simplified version of the Chebyshev filter. What are the assumptions here? I'll be dealing with just the one hop neighborhood alone, and I'll approximate the maximum value of the eigen values list from the Laplacian matrix to be 2. And I'll also rescale my adjacency matrix and the degree matrix, since the Laplacian matrix, the eigenvalues have a range between 0 and 2, which leads to numerical instabilities in the learning process. I'll be using the rescaled adjacency and degree matrix here. This is how you implement the rescaled degree matrix. I'll calculate it here, and I'll be implementing the modified normalized Laplacian matrix function here. I'll get the number of nodes. I'll add the identity matrix to my original adjacency matrix, calculate the degree matrix, and we have a function called DMM in the PyTorch package that deals with batch matrix multiplication. In PyTorch, the first dimension always represents the batch dimension. What do I mean by batch here? If you look into the previous lectures, we deal with mini batch gradient descent or stochastic gradient descent, where the batch sizes can be 1, 2, 32, 64 or anything to update the parameters. So PyTorch has a convenient implementation of batch matrix multiplication here. I'll run this, and this is how you implement the GCN layer from scratch using PyTorch here. The nn.module has the forward hook that lets us perform the forward pass, and I'll be initializing my a linear layer here with bias, the number of input features, the number of output features. Those are my hyperparameters. I'll calculate the modified Laplacian matrix, and I'll be doing the matrix multiplication with the feature vectors that's been passed through the linear layer. Linear layer is nothing but a single hidden layer in the feed-forward neural network. So let's build a graph neural network from scratch here. I'll be initializing my first convolutional layer with the input features, that is 7, the hidden dimension, which is again your hyperparameter, that basically the hidden dimension can be the number of neurons in your hidden layer, and I'll be initializing my second GCN layer here, and a final fully connected layer. And in between, I'll be using the dropout operation to set the weights, a proportion of weights randomly to 0. And this is how you do the forward pass here. First, while doing the first convolution, I'll take in my feature matrix and the adjacency matrix as input. I'll be applying the real activation function here, which is again an implementation provided in the PyTorch package. I'll be doing my second convolutional operation here. Again, apply the activation, do the dropout, and I'll be taking the average of all the features vectors for all the nodes, so that we have a single feature associated with a single graph. So this is what we call global mean pooling. And again, a fully connected layer, so that your final feature vector has the dimension according to the number of classes in your output. And then I'll initialize the model. Let's test the model. I have 25 nodes, 7 is my input number of features, and I'll be doing this unsqueeze operation so that we have a batch dimension of 1. PyTorch always deals with batch dimensions in the first element of the shape. Let's see, let's run it. See, this is my batch dimension here, 1, and the output number of classes, that's 2. Let's see what the output is. This is my output. I'll be defining the loss function from the PyTorch package. I'll generate random labels of size 1, since we deal with a single data point here. I'll initialize the optimizer with a learning rate of or step size 0.01. This is again a hyperparameter, and you can also tune the momentum and the weight decay parameter in the optimizer here. I'll run this example for 5 epochs. This is my random feature vector for 5 epochs. First, I'll reset the gradients in my optimizer, do the forward pass, calculate the loss based on the cross entropy loss that we have defined here, perform backpropagation, and update the parameters here. And I'll be printing the loss as training goes on. Let's run it. See, as the training progresses, you see a decline in the loss value here. This indicates that our model is working, the parameters are getting updated in the proper way, and since this model might overfit, since we are training it again and again on a single data point, and we'll be moving on to real benchmark datasets in the graph domain here. Based on the previous lectures, we'll be dealing with the enzymes and MUTAG dataset. The enzymes dataset is again a graph classification problem, where you classify a given graph into one of the 6 classes, 6 enzyme classes based on the enzyme commission number. What you have as features, so your features is basically a one-hot encoding representation of whether the node is in a helix, sheet, or turn. And the MUTAG dataset again deals with whether a given chemical compound has mutagenic effects on an organism called Salmonella. We have these 2 datasets. Let's run our graph neural network model. I'll be first defining a data module based on the PyTorch Lightning implementation here. I'll initialize my attributes here. What will be my batch size? What will be the number of workers, since Torch has a convenient multiprocessing function. I'll prepare my data here. TU dataset is a class from the PyTorch geometric library, and TU dataset has a lot of benchmark datasets for benchmarking graph based algorithms. So I'll be keeping my task here. Let's say my name will be enzymes here. If I want to extract the enzymes dataset, I'll get the number of node features, the number of classes here, and I'll be setting up my train and validation dataset here. And data loader is actually where the multiprocessing and batching of inputs happen. I'll pass my dataset, set my batch size, whether if I want to shuffle my dataset for each training epoch, the multiprocessing, and I'll be pinning my memory so that the data transfer to the GPU happens faster. Similarly, I'll be setting up my validation data loader here. Let's run the data module. Let's see how the dataset actually looks like. I've run it. If I access the edge index attribute from the dataset class here, what you get here is called a contiguous edge index here. So 0, 1 here indicates that node 0 and 1 is connected, 0, 2 means node 0 and node 2 is connected, and this is how the edge index is parsed in the PyTorch geometric package. Let's see what our attributes here are. So you have a list of nodes, and each node is a one-hot encoding representation of the type of secondary structure element. And this is your summary here. I have 19,580 nodes, each with a feature vector of size 3. This is my edge index, where I have around 74,000 edges, and these are my labels here for 600 graphs. This is again an implementation of the graph neural network, a very simple graph neural network that doesn't take into account the structure information of the graph. What if I do just perform just put a feed for a neural network for the features without taking into account the structural information? I'll initialize my linear layer here, another linear layer, and a final fully connected layer, so that it's projected to the classes dimension, the global mean pooling, or what I call the readout layer here, and I'll apply a final classifier with a dropout. How do I implement the GCN model here? PyTorch geometric has a convenient function for called GCN conveyor. Again, you supply the input number of features, the output desired number of features. I'll be defining 2 layers here, and again a final classifier. That's how it is. If I want to implement the graph attention layer, I have the cat count here, again 2 layers of graph filters, and again a final classifier. This is how you implement the graph sage convolution here. Where so this is all these models are organized into 3 main parts here. I'll obtain the node embedding based on the graph filters, apply the readout operation. I'll be averaging out all my feature vectors for all the nodes, and apply a final classifier. I'll be defining a class called GNN Lightning based on the Lightning model from PyTorch Lightning for training. So I'll have a method argument here that let's just define what should be the model that I want to use. I'll be defining my loss function here, and I'll be quantifying the performance based on the AUC ROC metric here. The task is multi-class, and I should also define the number of classes here. Self.net here represents the model that I want to use, and in the forward hook of this class, I'll put my model, features, edge index, and my batch number. I'll be defining my optimizer here with the default learning rate of 0.001. I'll return the optimizer here. In the training step, first I'll apply the model. For the batched input, I'll get my labels, calculate the loss. I'll be logging my loss so that we can view how the training progresses later on. PyTorch Lightning again has a convenient function called log that logs any metric of your interest. I'll update the AUC metric after applying the softmax activation on the prediction since it's multi-class, and I'll be comparing it with my true labels here. Again, I'll log my metric here. This is the validation step again, and in the training step, you'll be returning the final calculated loss. Resetting the gradients, performing backpropagation, updating the parameters, everything is handled by Lightning by default. You don't need to write those boilerplate codes here. This is the advantage of using PyTorch Lightning in combination with PyTorch. This I'll define my data module here. I'll define my model here. I want 64 to be the number of hidden dimensions, and a trainer class is implemented in PyTorch Lightning so that you can handle any device. You can train it on a CPU, as I'm doing here. You can train it on GPUs, you can train it on TPUs, or even multiple GPUs for large scale deep learning. And from the data model first. I have my trainer. I'll be using the fit function from the trainer. I'll fit my model and I'll pass my data. Let's see how this runs. So the number of parameters in my graph sage model here is around 9100. The Lightning module performs a sanity check whether everything runs perfectly by using the validation step hook, and after the sanitation check is done, it will start training.